Welcome, derivatives, third class. So this is jumping into page 24, exactly where we left off in the last class. And the whole idea behind this page, this whole mess of mathematics, is we're trying to get the slope of a function using the tangent line. And the only way to do that is to use the delta process, also called the derivative. Derivative is the slope of a line, or the equation for the slope of a line. And so we use our definition or our formula, put our function into it, expand it, cancel it, we get a nice new function, which is simpler. And that new function gives us the slope of the original function at any point. So let's do one more example. I'm going to simplify this first. It says find the derivative of this function, f of x equals -4 outside of x minus 2 all squared plus 4 using the definition. So it wants us to get the slope of this at any point. It's clearly a curve. It has different slopes at different points. By the end of this question, it's going to ask us, what is the slope here? What is the slope here? And what is the slope there? But I'll get to that later. First things first, use the definition to get the derivative of this. Well, I'm not going to treat it like it is. I'm going to expand it first, because if we don't expand it, life will become much more difficult. So if we expand this, we'll get -4 outside of x squared minus 4x plus 4. And if you simplify that, we will end up with -4x squared plus 16x minus 12. And it's much easier to do this whole process if we expand it first. So let me see, I'm just making sure that no one has any questions or who came in. Nasser, I think. Hey, Nasser, how you doing? So this is what we should start with. I'm going to take that and put it into this definition. And again, this is just a formula. There's no reason why you can't just take it directly like it is. Can someone remind me what this is? What is this? You know how to say it? That F thing? Because at the end of class yesterday, things got a little bit, there was a lot going on. So maybe you weren't paying close enough attention, or maybe I didn't even say it. If you want to know, we say this is called F prime. So if I use the word prime, that's what I mean. And it means the derivative. There's different terminology for it. So we're going to put our function in here. So just so I can be crystal clear, our function is going to be f of x, where we have a little addition x to it. Sorry, we have a tiny little, we're going to substitute x plus delta x into the formula. I'm actually going to call it h. We can cross that out and call it h, and then we're going to use the original formula. Let me just show you what I mean. So limit, as I'm going to say h approaches 0, because it's the exact same thing. I'm going to put in the original function, this function that I see here, but I'm going to replace all the x's with x plus h, just like we did yesterday. So -4, I'll show you, I'm replacing all of my x's with x plus h. That's the only change I'm making. Another x, I call it x plus h, minus 12. That's my first function. That's my f of x plus h function. And then minus the original function, minus -4x squared plus 16x minus 12. All right, so that is the hardest part of this question. Honestly, I believe that that's true. The reason it's difficult is because you need to understand what this f of x stuff means. But really, we're just substituting in the original function and the original function with a little extra thing added to the x. So now we need to expand this with our regular algebra rules. Okay, I'm just going to see who came in. I think Mohammed. Hey, Mohammed. So what am I going to do? Let's take it one piece at a time. This piece, I'm just going to expand out using regular algebra. This piece in the middle, I'm going to multiply through. For the last piece, there's a minus, so I'm going to multiply through, change all the signs of that, and I should be getting closer and closer to my final answer. So the limit as h approaches 0 of this. So I'll say -4. This is the same thing it was yesterday, 2xh plus x, sorry, h squared. I'm getting my x and h mixed up today, sorry. It's early in the morning. Plus 16x plus 16h minus 12 plus 4x squared minus 16x plus 12. All right, that's quite a big expression, but don't be alarmed. A lot of it will cancel. In fact, almost all of it will cancel out. That's my favorite part of this. Maybe I'm just a nerd, but I find it very interesting. I'm going to go ahead and make one tiny change here. Actually, let me see. Let me cancel some things out and see what we can do next. We have a 16x and a negative 16x. We have a negative 12 and a positive 12. And that's all we can do so far. I'm going to expand the brackets. I could have done that expansion all in one step, but I didn't want to. I wanted it to be clear so that if you have trouble, you can go back and watch. Let's do the top. If you know where I'm going with this, please try it yourself. You can get the final answer yourself now and compare it to mine. I'm going to multiply through by the brackets here. Minus 8xh. Be super careful with your letters. Minus 4h squared. We still have a plus 16h remaining. We still have a plus 4x squared remaining. And we have an h. And let me see here. Can anything else cancel? You should see that we have a negative 4x squared and a positive 4x squared. And now what can we do? What did we do yesterday normally at this point that made life easier for us? If you're with me, I know it's early, probably quite tired, but okay. What we're going to do is we're going to factor out the h, common factor. Perfect. Thank you, Mohammed. So the common factor here, just the h. We don't care about the numbers. They don't make a big difference, honestly. We don't need to take out the numbers. You could if you wanted to, but it's not going to help you. Just worry about those h's because we want to cancel them out. I'm going to show you a shortcut for this step that I didn't show you yesterday. I'm just going to zoom in here. We see that there's an h on bottom, and you can see that there's an h in this term, there's two h's in this term, and there's an h in this term. So what you're allowed to do, you can cancel out the h on bottom, and you had to cancel one h out of each of these terms. So one h, we can't cancel out this whole h here because there's two h's, so cancel one of them, it leaves an h, and cancel out this. That skips the step where you need to pull it outside and then cancel. Because you can do that in your head. Common factor the h and then cancel the h. You can do it all in your head. What you're left with is this. Right? Be very careful here. We're left with negative 8x, negative 4h, and positive 16. That's where those come from. That's the only things remaining in this expression. And now, this could have been one of the questions I did the first day. Just do direct substitution. When h is 0, this will delete. It will go to 0. And so we have negative 8x plus 16. That'll go to 0 because of this. All right, our final answer is negative 8x plus 16. So I think you'll agree, once you do a few of these, I know it looks like a lot of work, it looks crazy, but honestly, it's really not that hard. And I try not to say that too often because what I find easy is often very different from what a student finds easy. But honestly, most students don't have trouble with this once they've seen enough examples. So the interesting thing here now is, what does this equation mean? What is this? Can someone remind me what it is? Why did we do it? You know, we started with a big function, we got a smaller function. It's called the derivative. What's the point of the derivative? Like, what's the reason for getting it? Anyone alive out there? Too early? Did you hit the class button and go back to sleep? I'd like you to stay if you're gonna come to class. It gives us, yeah, not just the tangent line, it gives us every possible tangent line in the universe for this function. We can put in any x value, it'll pop out the slope of the tangent line at any point. So it's extremely, extremely useful. I'm just going to make a note here. This means that the derivative f of x, f prime x, is negative 8x plus 16. This can give us the slope at any x value. What that means is we can put any x value into it. It'll give us the slope at that point on the original function, which honestly is the most important concept in mathematics in a lot of ways, especially in calculus. It has a lot of applications for engineering, for physics. If you had the position function, you get the derivative, you'll get the velocity at any point. If you get the derivative again, you get the acceleration at any point. We'll see that later. But it's an extremely powerful function. But for now, let me just show you. Let's go to this. What's the slope at x equals 1? Well, we just plug it in. That means f prime, when x is 1, is negative 8. Substitute in your x plus 16. The slope when x equals 1 is 8. So that's this. That means the slope there is 8. When x equals 2, it should be 0 by the looks of it. Let's see what happens. F prime, when x is 2, substitute in your 2. It gives us 0. So that's 0 up there. Slope is 0. I'll go one step further. When x is 3, plug in 3 to the derivative. We get negative 8. 3 is our x value. The answer here will be negative 8. And we can see from our original graph that at the value x equals 3, it has this negative slope. It's exactly negative 8. All right? And you could choose any x value. You could do this all day. What about x equals 5, x equals 2, x equals negative 6, x equals 26, x equals 500? You can put in any x value. It'll give you the slope at any point. It's super useful. You never need to do that slope formula again once you have the slope equation. Okay? So derivatives are very useful. And in the next unit, we're going to use them a lot to figure out the special parts of graphs. All right, how do we feel about that? I want to move on to our basic derivative rules. I'm going to make things easier for you, is what that means. I know it's early, but I like to give you a chance to reply. Okay. At any time, just interrupt me. Not the end of the world. Okay. Hopefully you understand now the slope of a line can be found by using the derivative. That's all we're doing. The derivative is the slope. So let's go ahead. I was going to do some more practice. You can do these yourself. In fact, I just recommend that you do this one. The other ones are kind of challenging. I wouldn't ask them on a test or a quiz. You can try it yourself if you want a challenge. But this B here, I recommend you give a try before the assignment or before the test. It says, this is a very important note at the bottom of page 26. As you can see above, the delta process is very tedious. Like, it's a pain in the butt, is what that means, and time consuming. But when you actually look at the delta process for different types of functions, patterns come out. I'm just going to jump straight to the patterns, and we'll start working on the applications or the derivative rules so that we don't need to do the delta process every single time. You're only going to need to do the delta process when I ask you for it. So it says, algebraically and graphically, we can find patterns to the derivative that make the process easier. So we're going to make the process easier. This is just saying that there's different ways of saying what the derivative is. There's many notations for derivatives. You can see dy by dx, y prime. You can say d by dx. That also means derivative. F prime, they all mean the same thing. That's all this is trying to say. Let me get to our first rule for derivatives. The constant rule for derivatives means that if you want the derivative of a constant, it's always 0. Okay? Let me show you what I mean by that. Let's just say, before I look at the graph, for example, if y was 5, what's the derivative of 5? It's 0, because it's a constant. What if y was 2 pi or pi? What's the derivative of that? Well, pi is a constant. The derivative would be 0. No need to do the delta process. Take it for free. What if y was e or 2e? You know, e is just a constant as well. Y prime would be 0. That's what it's saying. Constants, they just get deleted. The reason for that is let's think about what a constant is. Let's think about it in terms of our fancy Desmos. I just want you to be able to see this very clearly. What is a constant on a graph? Well, look at this. For example, let me just put in any constant, a. Sorry, my keyboard is freaking out as usual. Let's put in y equals a. Sorry, I'm thinking about C. I want it to be a constant. Why is it making my life difficult today? Anyway, I'll just draw it. This is y equals 2. You know, if you use your imagination, I did my best. Y equals 2, that's a constant. What's the slope of that line? If you were to put a ball, like put a soccer ball or something on this, it wouldn't move. The slope is 0. That's why the derivative is always going to be 0 for a constant. Even if you used, you know, if y was 6, the slope would be 0. If y was negative 2, it's still going to be 0 because it's a constant. Nothing to it, right? So that's what I'm trying to get at here. The derivative of a constant is always 0 because the slope of the line is 0, especially if you look at it. So let's just jump around here. Let's see how this works in practice. Very simple. I've got a note here from limits. We can see that these derivatives follow a pattern. Let me just show you why it works. From the delta process, the limit of some constant. So let's just say the function was f of x. It would be it would be x plus h minus x over h. You would have your x's would cancel, and then your h's would cancel, and you would be left with 1. That's just the very basics why it works. The derivative of x squared, that's a little bit different. That gives 2x from the previous pages. But let's not get too confused here. I'm just going ahead and showing you that there's some patterns. It says derivatives follow a pattern. The patterns are, if you have a constant, derivative is always 0. If you have a power, that power actually does something really neat. The power just, you know, I'll write it out more clearly. If you have the function x squared, its derivative, you just take the 2, bring it down, and then reduce the power by 1. So you end up getting 2x, and then what's 2 minus 1 on top? It's 1. So there's a pattern here. You don't need to do the delta process. It comes out easily. All right, let's formalize this. So first things first, the constant rule. I'll be talking about that a lot. For a function where f is a constant, c is a constant number, their derivative is always 0. For a power, when you have a power, it's called the power rule. a variable raised to a constant power. It's trying to tell you that if it has a power, the power comes down in front, and that's reduced by 1. Look at this. The n comes in front, and we reduce the power by 1. Let me give you a very simple example. Let's say we had x to the power of 7. The derivative, take the 7, move it in front, becomes 7x, and then reduce that power by 1, 6. You're done. Isn't that the best thing ever? You don't need to do the delta process for that. You just use the power rule. It'll give you the slope function. So that's like one of my favorite rules in all of math because it's like hilariously easy. Okay, so hopefully you see what I mean here. If the power was, let's just say x to the power of -3, you'd still do the same thing. What would happen? We would end up with, bring that up front, we end up with -3 x. What's -3 minus 1? This is a real test now. What's -3 minus 1? Yeah, you'd be surprised how many people get that wrong. -3, it's already negative. Minus 1, we're making it more negative, so -4. That would be your final answer. Good job, Yaya. This is the final answer. All right, let's use these rules. Find the derivative of the following. What's the derivative of this? For the example 5. It's 0. What's the derivative for this one? It's e. E is a constant. It's 0. What's the derivative of this one? If a power is negative, it will never get to... Here, 1 second, Mohammed, I'll answer that. This is still a constant. You know, we can figure out what that value is. Sine of 2 pi is 0 already. But even if we didn't know that, this is a constant. And so the derivative f of x, f prime of x is still 0. Because they're all constants. Okay, Mohammed, you said if a power is negative, it will never get to 0. I'm not entirely sure what you mean. Could you reword that so that it's more clear for me? Oh, if you have powers, yeah, if your function has a power in it, like it's a polynomial, so you have an x or an x squared, x cubed, x to the power 4, it doesn't become 0. And the reason for that is, look, just look at this function here. Let's make a simple function. Remember that it's the slope. What we're getting is the slope of these. So let's just say we had y equals x. That function, no matter what x value we choose, has a slope. The slope can never be 0, okay? The general function won't be 0. If you had x squared or some version, we have slope. All of these points have a slope. Over here, it's a big negative slope, 0 slope, positive slope. We're not going to get 0 for all possible values. That's all. Yeah, you said, can I explain C? C just means, oh, you mean the number C here. You mean this C. To put it simply, the derivative of a constant is 0 because a constant line looks like this and its slope is always 0. This, you know, C here, sine of 2x is not a function. Sine of 2x is just a number. So its derivative is 0. It's a constant just like the others. Is that okay? Do you see what I mean? Yeah. So let's go ahead and use the power rule. Let me make a note here. This is going to be all power rule. Power rule, I call it power rule because we're looking for the power. And then once we see it as a power, we can bring it down in front. So this, what's the derivative of this first one? We don't need to use the delta process. All we need to do is take the 3 and move it down in front. 3x. Change the power, subtract by 1. Done. Easy peasy lemon squeezy. It's like the best. It's the best. This one, we don't need to use the delta process. It's just 8x to the power of 7. Done. You can put in any x value. It gives us the slope of that original function at any point. We don't need to even do the slope formula anymore. What about this one? This one's a little bit tricky. Maybe it's trying to trick us. What's happening here? Well, this is still the power rule, but let's just think about this. This is x, which is really x to the power of 1. So the 1 will come down. So it comes down. It stays x. What's 1 minus 1? Well, it becomes 0. So the final answer here is 1. It's a little bit tricky. That one's a tricky one. Abdullah, you said 1 over x. I think you're thinking a slightly different case. So you just, that's a special case. Make a good note of this one. It'll come up again though. And then f prime of this one. What's this going to be? Well, the 2 comes in front. And then this is technically 1 minus 1. So we would just say, sorry. 2 minus 1, which is just 1. Okay. So if it says to the power, x to the power of 1, you can skip directly and just call it an x. We know it has a power of 1. It always has a power of 1 if it doesn't have another number next to it. So let's just come straight to that. Okay. So the power rule, I hope you'll agree, is not overly complicated. There's not a whole lot to it. Let me give you a couple more examples of this middle one. This one here. What if you had y equals 7x? Well, if it has a power, it's easy. You bring it down in front. If it's just to the power of 1, we just see that it has a power of 1 here. Just delete the x is really what we're doing. You would bring the 1 in front, which doesn't change anything. It just comes out, you just keep the 7, all right? That's how these things work. Let me do another example. What if it was 12x? Well, the derivative would just be 12. These are nice and simple questions. And it's fundamental. How do you feel about the power rule? Are you happy that it's gotten easier? Yes. I thought you might. I want to make a note. You can jump straight from this to here. You can jump straight from this to here. There's no reason to show the work for those intermediate steps. You'll get so used to them, you'll be fine. Okay, you'll be fine. And just don't forget that this is a slope function. We can always put x values into this now. We can get the slope at any point of the original function. Don't worry too much about the extra stuff. I don't want to mess with adding stuff. I just want to talk about the rules today. So the constant multiple rule. It means for a constant a, let me show you as an example the constant multiple rule. It means that if you had something like this, all right, you have 4x cubed. You can still bring the power down in front, but if there's a number already there, just multiply them. So the derivative, what's 4 times 3? It's 12. And then reduce the power by 1. So if the number's already there and it comes down next to it, they just multiply. It becomes 12. If it was a different number, it would just multiply differently. Let me give you another example. Maybe a little trickier. What if we had something like this? throw you off here. Maybe you can you handle this? You've got a bunch of different things next to each other, but all it means is we do the derivative of them one at a time. We don't, can you imagine doing the delta process on this? You would want to jump off a bridge. But for the simple rules, it's super fast. Okay? Let's use the power rule on every single one of them individually. This one, this one, this one, this one, this one. 5 different rules. Let's see, the first one, 3 comes down, multiplies with the 5. 15, reduce the power. That one's done. The next one, the 4 comes down, multiplies with the 2, becomes 8, reduce the power. 8x cubed. 3x, well, we know from before that if it's just an x, it just gets deleted because the 1 comes down, it becomes 0, it cancels itself. So this is just 3. What's the derivative of pi? Well, pi is a constant, so it becomes 0. Derivative of 1 is also a constant. One and 1 are constants, so they come out to 0. Okay, this would be pretty much our final answer. The derivative of the original function, or the slope function, is this. I'm not going to bother rearranging the powers, but you could if you wanted to. So yeah, you said 10x squared. Which, was that for a different answer? Am I missing something? Yeah, so your answer would be 10. Let's keep on going. Most of these rules have different names, but it's just things that are almost logical, okay? So it says sum and difference rule. The sum and difference rule just means that if you have things that are added and subtracted, so sum and difference means plus and minus. So if you see pluses and you see minuses, you have polynomials, it doesn't matter, you just do the derivative of each term one after the other, just like I did before. The only time that this power rule makes a problem for us is when it doesn't look like there's a power. So for these examples here, you know, for example here, that doesn't look like a power, this doesn't look like a power, this doesn't look like a power, and this doesn't look like a power. But we can force it into the power form. So we want to change them to power form. And you just need to know a little bit about math. What is x, the root x? Well, the square root of x is x to the power of 1 over 2. And now it's in power form because it's a number and an x and then a power. In this case, just an x with a power. So bring the power down. Take this 1/2, bring it in front. So the derivative is 1/2 x. And what's a half minus 1? What's 1/2 minus 1? Well, you can do it 2 ways. You can say that it's negative a half. The way that I like to think about it is, yeah, the way Yaya said it. It's the same as 0.5 minus 1, which is negative 0.5, which is negative 1 over 2. So negative 1 over 2. So yeah, you got that. The one thing I will say is that this question isn't done. We need to put it back in proper form here. So what we'll do is, I'm running out of space. Once again, I don't know who made this book. It will look like this. Keep the 1 on top, 2 stays on bottom. This negative, we bring it on bottom and we change the sign. Okay, negative, no negative. Let me just steal a little bit of the space. So this would be your final answer. That would be perfectly acceptable, or this one. All right, no big difference. Sorry, I ran out a bit of space there, but actually we're not going to do 2 right now, so it doesn't really matter. Let me rearrange this so that it's a little easier to look at. Sorry, this is for your benefit later. If you have any questions for me, yeah, type them in the chat. I'm gonna shrink these down. Sorry, I probably could have done this later. I want to make sure that when you look at this later, it's clear for you. All right. So Abdullah said -1 over x squared. That's for this one? Or are we looking at something else? I'm going to try.
Actually, I solved the first one and the second one. 1 over x, it's -1 over x squared.
Yeah. I'm not sure why I'm. Yeah. I ran out of space, but 1 over x is x to the power of -1, which would then, the derivative would give -1 x to the power of -2, which is -1 over x squared. But we're going to cover that more later. That's why I didn't bother to do it now. I guess I did it now.
Okay.
So this one here, I'm not changing the form. I'm not getting the derivative yet. I'm just going to change the form. This is x multiplied by x 1/3. So the root 3 is the same thing as saying power 1 over 3. And the reason I know I need to change that is because in order to use the derivative, I need it in power form. The other problem here is that this is a product. And we can't currently do derivatives of products. We will by the end of the day, but right now we can't. So let's go one step further and simplify them or multiply them together. This is x to the power of 1. What's 1 plus 1 over 3? You put it in your calculator, it's 4 over 3. Or another way of thinking of it, the 3 is added. You have 1 plus 3. Anyway, I'm not going to get into that right now. You just add 3 to the top. You get x to the power of 4 over 3. So Abdullah, you said 4, x to the power of 1 over 3, all over 3. That sounds about right. Just let me recap what I just did. I needed to force it into power form, so I figured out what the root is as a exponent, and then I added the powers. 1 plus 1 over 3 is 4 over 3. Let's get the derivative. Same rules apply. The 4 over 3 comes down in front. Becomes 4 over 3 x. What's 4 over 3 minus 1? Well, the shortcut is take the 3 away from the top. So just take 4, subtract 3, it'll give you your power. 1 over 3. So this is how I write them. I like to have it in the form where I have a constant in front and then my x terms separately. If you start mixing them, it's harder to do derivatives later. All right? So this is how I write it. Abdullah, I have a feeling maybe you wrote it like this, which is still perfectly right. There's nothing wrong with that. But then it becomes less clear where the constant is and where the function is. You see what I'm saying? So for derivatives, it's usually best to put the constant in front and the function after, the x part after. Final answer here. All right, hopefully you're keeping up. Let me know if you need me to slow down or redo something. There's a lot of little tiny rules here. Let's see the first one. First things first, we look at this. Is it in power form? Well, clearly not. There's an x on top, there's an x on bottom. What are we going to do here? Well, we need to force it to look the way we want. So there's nothing to do on top, but on bottom we can fix it. On bottom we have x to the power of 1/2. But we don't want fractions. We want it in power form, which is just an x with a power, maybe a constant in front. That's all. So bring it up top. That will make x times x to the power of 1/2, bring it up to the top, but we can't do that for free. So we change the sign, make it a minus. Let me get this out of the way. And then what do? Well, we still multiply, add the powers. This is a 1. What's 1 plus 1/2? It's 1/2. So sometimes we need to force it into the form that we need it in. We need it in power form. But once it's in that form, life gets much easier. Okay, so once again, if there's x's on bottom, just put them on top and change the exponent to a negative. Flip the sign of the exponent. If it's already negative, it becomes positive. And then we have it in the form that we want. So this is, I'll call it power form. It's a good thing. 1/2 root x. Yeah, as long as the root is on bottom, that's perfectly well. So let's do the derivative. So let me rewrite it. The y is x to the power of 1/2. The y prime is, bring the power down, keep the x, and well, actually, this is the same thing as we had in the first question. It must be the same, yeah? So -1/2. And we don't want that form. We want to simplify it a little bit. It's 1/2 root x. You can keep the power the same if you want. For those of you that are a little bit confused as to why that is, just consider this. This is x to the power of -1/2, which is the same as 1/x to the power of 1/2, which is the same as 1/root x, which is why I have this root x here. So a little bit of algebra, but the derivatives themselves are not that hard. And the delta process would have been way, 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 way harder. All right. So it's much faster than the delta process is what I'm going to say here. Much faster and simpler than the delta process. Okay, before we move on, I've got a couple more rules to throw at you. They're all sort of equal difficulty. How do we feel about this? This is the fundamental part of derivatives. Like, this is the first rule you need to know, the most important rule you need to know, because the way derivatives work, you learn one thing, and then it builds on it, and it builds on it, and it builds on it. I guess most times we build up top. So power rule, then we're going to have product rule, quotient rule, chain rule. And then that's basically it. Did you have a question? Okay. All right, I thought someone said something. Maybe you were talking to like a cat or something. All right. Find the derivative of each of the following. Let me show you how fast these are. First of all, these are all in power form. These are all in power form. These are all in power form. This is the only one that's going to cause us any difficulty. So I'm going to do them. I'm going to show you how fast we can do these. Derivative. Oh my goodness. Sorry about that. Y prime, bring the power down, reduce it by 1. 7. Done. E. What's the derivative? Bring the power down, reduce it by 1. Bring the power down, multiply it. So 3 times 3, 9. The next one, bring the power down, reduce it by 1. It becomes 1, so don't write it. This one, be careful. This is a -1x to the power of 1. If you bring that down, bring that down here, it multiplies, it just becomes -1. You reduce the power, becomes 0, which is -1. But really what I would do, if I were you, I would just look at the constant. You see that it's just an x there, just delete the x. It leaves the -1. And then this is a constant. And they go to 0 when you get the derivative. So it gets deleted. How's that? Did I do that too fast? I'm going to assume not. I'm just giving you my shortcuts. You'll find that you can get faster and faster at this. What's the answer for this guy? Someone give me the answer. It's our derivative. Maybe not Abdullah. Abdullah's killing it today, but I want someone else to show me that they're alive. What's the derivative going to be? Two minus 12x squared. Well done. Thanks, everybody. You're alive. I'm so happy.
Just one, just one of my friend, they call me and I get busy a little bit.
It's okay. It's okay.
And every day I sleep in your class.
Okay, how do I start D? You know, we want to force it into power form. It's not in power form. So we want to change it to power form. Just bring it would be perfectly fine if that x was on top. So we just say 2, bring the x up top, that's fine, keep it squared. We just need to add a minus, we just need to change its sign. And now it's in power form. So the derivative, y prime, negative 2 times 2, right? We take the negative 2, multiply it by 2, becomes negative 4. Reduce it by 1. Negative 2 minus 1 is more negative, negative 3. And then you should write it in simplified form. So just take the x, take this, bring it back down on bottom, and change the sign again. I'm going to say these are both okay, but the final answer is better. It's more clear. You don't have negatives in the powers. It looks more like what you started with. Okay, so that's our fundamental rules for how to do these derivatives. Good, all good? Hopefully you're happy, once again, that it's a little easier to understand than yesterday's class. And it doesn't get that much harder. We're over the hump. It's like tricky, 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 complicated, confusing, confusing. Oh, these rules are pretty easy. Let's do one of these. It says find the slope of the curve. The curves are these. At the given point, or at the indicated point. So for the first question, it says find the slope of this 9x minus x cubed at the point 2, 10. So this is just a two-step process, okay? I'll just give you the 2 steps. First thing you need to do, if you need the slope, you of course need to find the derivative, because the derivative is the slope function. The second step we need to do is just sub in the given x value, and that'll give you the slope at that point. All right, so let's do the 2 steps. First step, what's the derivative of this? It's 9 minus 3 x squared. That's our derivative. The second step, I'm just going to say when x equals, let's see if we're paying attention. What are we trying to do here? We're trying to put in an x value. We've been given an x value. It's 2. So when x is 2, we just substitute it in. The derivative, or the slope, equals 9 minus 3, 2 squared. And then what's 9 minus 3? Well, it's 2 squared is 4. 4 times 3 is 12. It's 9 minus 12. It's 9 minus 12. I guess it's negative 3. That's the slope at the indicated point. Let me show you graphically what this means. Some students, I know when I graph, you just turn off. But graphs are extremely helpful for understanding what's going on, okay? So I'll leave this here. I just want to compare it. I'm going to put in my graph here. I'm going to say y equals 9 minus 3x squared. this is that function. Okay, this is the function. And actually, I'm going to go one step further. I'm going to use the tangent that I did yesterday so we can see the exact slope. So let's see. Let's put in the function 9 minus 3x squared. This is that function. I want the slope when x equals 2. So clearly this function has different values depending on where the x is. So the slope here, let me turn the tangent line on. The tangent line down here is very small. Let's see when it's 2. So right there. That looks like 2. X equals 2. Yeah. So it should be very, very steep in the negative direction. And that's what we're getting, -3. And look, Desmos is telling us, it should be telling us that as well. At 2. Let me make sure I've got my value in correctly. What's going on? Well, I think I might have something wrong with the math of it, but the idea is that that's our slope. It should be -3. I think I maybe made a tiny little mistake here. I'm not sure how, I'm not sure why, but hopefully you can see the concept. Let me just check and see using my notes. Yeah, slope should be -3. Anyway, it's not a big deal. Maybe it doesn't match for some, maybe I typed in the calculation wrong on the Desmos side of things, but the concept is perfectly fine. This is our y equals, 9 minus 3x squared function. When x is 2, we see that it has a very steep slope in the negative direction, and that steep slope is -3. We could put in any value. We wanted to figure out what the slope is at x equals 0 to give us that too. Oh, I know what I did. I know what I did. I typed in the derivative. I'm a silly Willy. I'm a silly bear. Look at this crazy function. Let's put x equals 2. Some of you are long since caring, but that's okay. 2. Slope of the line at 2. The tangent is 3. All right, I feel better now. Slope of this line, tangent, -3. That's what our function does. Sorry for taking you on a ride that probably wasn't all that exciting, but it's important stuff. This function, this blue function, is the original function, and we've gotten the derivative, which can give us the slope at any point. So we just put our x value in, and it gives us the slope of this green line. It's pretty cool. Like, if you appreciate math, that's pretty important. And it might not seem like it now, but this is one thing that actually is used in real life. If this, for example, was a formula telling us about the position of someone in terms of time, we get the derivative. This would be the velocity function now we would get. Get another derivative that gives us the acceleration of that person. Or this could be, for example, current in a circuit or charge in the circuit. If you get the derivative of that, it'll give you the current in the circuit at any time. So these are all things that are actually applied. I'm not going to get into that much more now, but just believe me that calculus is used all over the place, everywhere from electrical engineering, mechanical engineering, to video games and space launches and sports, all sorts of stuff. Believe it or not. All right, so let me see. I want to choose an example here to have you do, just to see if we are on the right track here. I want you to try C. I'll stop talking at you for a minute. You can try C, and then we'll pick it back up. Just take 2 minutes to try to get the answer for C. I did the first step for you, just in case you're not sure how to simplify that. Boom! 4/3 it is. We're going to start getting into a point in this course where my answer, my final answer, not the number, but the derivative form, might look slightly different than yours. That's not a big deal. For example, some of you might have simplified down to this. Some of you might have written it as a root. Some of you might have left it like this. It's okay. They're all the same thing. As long as you've done the derivative and the numbers are where they're supposed to be or the powers are correct, it'll all work out to the same final answer, which is what's nice about this. So just make a note, we're putting in the x value into the derivative. That's this x value. It simplifies down. So it's pretty neat. I'm going to take one more kick at the bucket here and show you that this is true. And because I feel like I need to redeem myself after failing so miserably doing this before. Let me put in the original function for x to the power of 2/3. And let me take out the tangent. This is our function. For those of you, if you appreciate math, this is a very ridiculous looking function. It's what happens when we have like cubic roots and things like that. But this is our function. It's like two arches. We want the slope when x equals 8. So let's turn on the tangent line. I'm going to set our value to 8. The tangent line should be 1.3333333333. So the slope at that point, when x is 8, should be 1.33333. And it is. So this is our function, the blue line. The green line is our tangent line. And we can see that its slope is 4/3 at that exact x value. Okay. When x is 8. So maybe you're starting to appreciate how interesting this actually is, or how much easier it is to do it than to even do the original slope formula or do the secant line. Just because it's calculus doesn't mean it's difficult. If anything, it should be easier because that's why Isaac Newton came up with it. Anyway, hopefully you're appreciating that, and if not, it's okay. You can just work out the math. Right, the rest are all basically the same idea. You can try those yourself, okay? What I will say about this one, well, I'll ask you, would you like me to do another example of this, or do you want me to move on to the next topic? You know, do you want me to do D, or would you like me just to move on to the next extension? I'm gonna wait for one or two more answers. So Bill, the next topic. Anyone else? Do you want me to try one more example, or do you want me to do next? Okay, let's do the next topic. You should try this. Definitely try it before the assignment. But I could give you 100 of these. They'd all be slightly different. It's just the way it is. All right. The next area is practice. I'm not going to do these. The definition of the derivative is just the delta process. The full solutions are online on D2L in course notes, yeah? So you can find it anyways. The rest, you can see you would do them, you would be able to handle them, no problem. 3 is like we just did, so nothing special there. Let me give you what I feel like are like my favorite derivative rules, because they look so difficult and they make these giant functions, but it ends up being really simple, okay? And it's called the product rule. And I'm essentially going to tell you to skip pretty much all of this because I don't want to spend the time working through that. I just want to show you this part. If you have two functions, then you can, you know, if you have a function that's made of both of them multiplied together, let's just say we have both of them multiplied together. This is a bad example. Let me just call this y. Let me just say we have one made out of f and one made out of g. We can get the derivative of that without expanding it. There's a rule for it. we just need to note that this is the first function. This is the second function. They're being multiplied, so it's a product. And we just apply what's called our product rule. We're going to jump down and get to the point. The product rule. When we have two variables multiplied together, or two functions really multiplied together, variables is not a very good way to put it. Two functions multiplied together, we have what looks crazy but is actually very simple. Follow me here. I'm going to be very clear and say it very slowly so you can all understand. The derivative of one function multiplied by another function is the derivative of the first function times the second plus the first function times the derivative of the second. In other ways, there's another way to say this. I'm just going to make it as clear as I can. This is our first function. This is our second function. A good pattern to help remember the product rule is this. Derivative of the first times the second. Whoa, why is that so big? Derivative of the first times the second plus the first times the derivative of the second. Okay? Whatever the function is, you get a derivative, and then the second. I'll just show you what I mean. I'll give you the examples, okay? So this is the way that I always remember. First, derivative of the first times the second plus the first times the derivative of the second. Let's do an example. First things first, find the derivative of this. You could expand it, let's not. Let's do it simply. Let's just label them. This is the first. This is the second. What I like to do is say, okay, the first function is 2x squared. So the derivative of the first function is 4x. All right? The second function is 3x cubed. The derivative of that function is 9x squared. Okay? I have everything I need to do the product rule. This is a product rule question. Product rule is going to be the derivative of the first times the second plus the first times the derivative of the second. Just substitute in your answers. What's f prime? It's 4x. What's our second function? The original second function, 3x cubed. Plus, what's our first function? 2x squared. Let me put in brackets here just so that everything's split up. What's the derivative of our second function? Yx squared. And this is done. This is the derivative function. We don't need to expand it unless it asks us to. I mean, of course, you can simplify it if you want to, but this is the basics. So first function, first function, first function. Second function. Sorry, not the second, the derivative of the first, and so on. Can you see what's happening? I feel like I didn't explain that clearly, but I think you can see it with the colors. Two functions. Derivative of the first times the second function, plus first times the derivative of the second function. You don't need to simplify. I'm going to expand it just so you can see what would happen. If I multiply this out, you would get 12x to the power 4 plus 18x to the power 4. If I add those together, you get 30x to the power 4. All right? So you could go one step further and get that answer. The reason I want to show you that is that for some of these questions, we could have expanded this. And then for this question, it would be very easy. For other questions, it would be a huge, huge pain. I just want to show you that it would give you the same thing. So if we expand this, multiply it out, it gives 6x to the power of 5. The derivative of that is 30x to the power of 4. I should just say that the derivative this way and the derivative this way is the same. The problem is sometimes it's very complicated to expand it first, right? So before I move on, any questions on that? Because they're going to seem more complicated, but the rule, we're still going to use the same rule over and over and over again. Oops. Hopefully it's okay. Let's keep going. So how do we know when to use the product rule? Well, I know definitely I'm going to use the product rule for this next question. I know it because I can see there's a first function, and I can see that there's a second function, and I can see that they're multiplied. So if we have a first function times a second function, we're going to use the product rule, which is the first derivative of the first times the second plus the first times the derivative of the second. So you don't need to write them out first. You can actually write it directly. So the derivative, what's the derivative of that first function here? Well, I'm looking at this one. The derivative is 6x squared plus 3. I've done the first part. What's the second function? Well, I don't change it. I just keep it the way it was. X to the power 4 plus 2x squared minus 6. That's my second function. Plus the first function, unchanged. It's this part done. And then the derivative of the second function. So it's all power rules. I'm doing this part. 4x cubed plus 4x. And then what's next? Excuse me. Derivative of -6, it's a constant, and so it becomes 0. So we don't need to write anything else. This is done. Derivative of the first. Times the second. Plus the first. The derivative of the second. Can you imagine doing the delta process on the original function? You'd be here until next Sunday. But if we do the product rule, it's very straightforward. Any questions still alive out there? How are my fans doing out there? I know you're not my fans. You're my students, but the man can dream. We're good, okay. I think you're good too. I really like you guys, and ladies, obviously. I don't mean to forget any of the ladies in here. I still see you, Sarah, Yasmin, Aisha. When I say guys, I mean in the general sense. People, folks, humans. So, power rule is pretty sweet. Not gonna lie, it's pretty sweet. Let's do one more example of it, and then I'm gonna show you 2 more ways to do things. Find the derivative of each of the following. It says simplify the results. So I didn't ask you to simplify. Let's see, let's try B. I don't know, A or B, which one? Maybe I should flip a coin. We can see that this would be the first function here, this would be the second function, this would be the first function, this would be the second function. Let's do B just because it looks a little bit trickier. A you can do on your own. So for B, let's see. Let me write out the first function. Or I'll just write out f prime. That would be 3. Let me write out s prime. I can see that that's 8x. All right, I already know what f and s are. This is my first function. This is my second function, also known as f and g. Same thing if you want to use that. But this is what we do with the product rule. So we just plug it in. Let's not forget what the product rule is. It's the first derivative of the first times the second plus the derivative of the second. I'm just plugging it into the formula. the derivative of the first is 3 times the second, unchanged. I'm going to use brackets. Sorry. Let me rewind. Derivative of the first, 3. Second, unchanged. Plus the first, unchanged, times the derivative of the second, 8x. Not so bad. All we need to do now is, if we need to simplify it, we need to expand. So I'm going to take the first set, expand them. I'm going to take the second set and expand those. I should have written this as the derivative. Derivative is 12x squared plus 9 plus 24x squared minus 16x. And I'll simplify this. This is 36x squared minus 16x plus 9. I probably don't need to write this out, but that's that piece. It's that piece. That's that piece. So this is my final answer. How do we feel on a scale of 1 to 10? 1 being terrible and 10 being, it's a good Thursday. Got an 8. 8's good. I'm happy with 8. I'm feeling about 8. Maybe 7, maybe 6. I'm in the middle of moving. It's kind of a pain. I don't like moving. My house is coming down around me. But we still continue. All right, well, at least it looks like the average mark in this chat right now is above 50. So that's what I like to look for. Long story short, we have 3 rules really now. We have rules for constants. If it's a constant, it becomes 0 when we get the derivative. If it's got a power, we use the power rule. And if it's a product, which is 2 functions multiplied together, we use the product rule, which has a simple formula. All right, so that's that. The next question here, I'm not going to do the whole thing. I'm just going to talk through it. It says that we need the slope of the tangent to this curve at x equals -1. So all you would do, the first step would be the same thing as we did before. Whenever we do the slope of the tangent to the curve, we're doing the same process. Find the derivative. So use the product rule. And then substitute in x into that answer and see what you get. I'm not going to do that because the full solutions are online and there's not a lot to it. I want to get into the next rules, okay? Okay. So what if, these are all practice, they're all basically the same. What if you had not a product, but a quotient? Quotient meaning one product divided by another product. Well, we still do the same thing as the product rule. I'm just going to skip all this, except we have a slightly new formula. Quotient rule. We have 2 variables dividing each other, also known as 2 functions dividing each other. We have this rule. Follow me here. One function divided by another function. You get the derivative of the first function times the second minus the derivative of the original function times the derivative of the second all over the next one squared. Let me simplify it for you. This is how I remember it. You have the top, the derivative of the top times the bottom minus the top times the derivative of the bottom all divided by the bottom squared. All right, it's essentially the product rule. Let me write this down. The product rule was this. The quotient rule, I know it's right above, but let me just write it down next to it. It has the same structure. The only difference is it has a minus where the plus used to be, and it has this bottom term here. So don't get them mixed up. The product rule ends up giving you only products. The quotient rule ends up giving you a new quotient, a new division. But I wouldn't say it's any harder, it just looks different. Okay? The other way we can look at this, some students prefer to see it this way. It's fg minus fg prime over g squared. They're the same thing. In fact, I should have said that for the product rule earlier. I'm just going to scoot up the page just so I have it in my notes. It's also known as f prime g plus f g prime. And some students prefer to do it that way. It's up to you. Let me show you some examples. So when you look at this, I would hope that you would look at it and be like, oh my God, I can't imagine doing that with the delta process. Because you would have to put in x plus h and x, and it would just be a complete nightmare. But thankfully, we have a rule for this. It's called the quotient rule. Let me try to make it as clear as I possibly can. We know that our f, or our top, is 3 minus 2x. F prime is negative 2. G, our bottom, maybe I'll call it T and B, top and bottom. You can call it F and G, it doesn't matter. Top, bottom, derivative of the bottom, and I'll color code it so that we're consistent. I'm just setting those up so that we're very clear what's what, okay? So we have the top, the derivative of the top, the bottom, the derivative of the bottom. And what's our product rule? Sorry, our quotient rule. I'm even getting it confused now. It's the derivative of the top times the bottom minus the top times the derivative of the bottom all over the bottom squared. And you don't need to simplify this unless I'm asking you to. You can just put it directly in, you know, slot it in, and we're done. Hello. Thank you. So all of this is just set up. I'm going to slot it in. Just put our numbers in. So negative 2. I'm looking at this part. Negative 2 is our derivative of the top. What's the bottom? The original bottom? X squared plus 2. Now I have to go minus top times the derivative of the bottom, which I've already done. It's 2x all over the bottom squared. So just take the whole expression like it is and square it. So I'm going to highlight some things here so that it's clear what piece is which. Derivative of the top minus, or sorry, times the original minus the top, derivative of the bottom, all over the bottom squared. Okay, so I just want to make sure that you are making these connections here. It's not difficult, we're just like getting the puzzle pieces. The top, the derivative of the top. The bottom, the derivative of the bottom. Piece them into your formula, you're done. If I don't ask you to simplify, don't simplify. This is your final answer. Okay? How do we feel about that? You might not love it, but hopefully it at least makes some sort of sense. dot. Sorry, I'm just looking through my notes here. Let's do one more. In fact, I want you to try the next one. Try this. We need to get, I'll call it F and G, just so you can see different terminologies. You need F, F prime, G, G prime, or you can do it as you go. I just like to list them. And then use our quotient rule. All right, take 2 minutes, come back to me with the answer. You can try to type it, or at least, do your best. Are you getting anywhere with this? It's probably a huge pain to type out the final answer. 6x squared, is that really what the answer comes out to? Oh, that's F prime. I see now. Oh, I feel silly. Okay. So these are our F prime, G prime. Our quotient rule is as follows. The derivative of the top times the bottom minus the top times the derivative of the bottom all over the bottom squared. No need to simplify. Unless I specifically ask, there is zero reason to simplify that. It's not going to help you at all. And hopefully you can see that we have all the pieces. It's done. Someone is just calling me, sorry about that. So that question's finished. Hopefully it's clear where every piece came from. The derivative of the top times the bottom minus the top, derivative of the bottom squared. I'm going to do one more example, then we'll do the chain rule, and we'll be done for the day. This one. So it looks complicated, but again, when we look at this, we see that it's a quotient. You know it's a quotient because you have one fraction here. You have a function divided by another function. You're going to use the quotient rule. So let's see what happens. We want the slope of the curve. So if it says we want the slope of the curve, the first step is get the derivative. Second step is going to be substitute x. Substitute in your x value. Let's do it. Y prime is the derivative of the top, 6x, times the bottom, 2x squared minus 1, minus the top times the derivative of the bottom, is 4x, all over the bottom squared. Okay? Top, derivative of the top times the bottom, top, derivative of the bottom, bottom squared. That's our first step. Our second step is we need to substitute in our x value. It's going to be a bit of a pain, but it's going to be a whole lot easier than if we try to do it by the delta process. So we're going to say when x equals -1, y prime is, and we just substitute in, 6 times -1, 2 -1 squared, minus 3 -1 squared, minus 5, 4 times -1, all over 2 -1 squared, minus 1, all squared. And you could actually put all of that into your calculator if you wanted to. It would be obviously a little bit of work, but not difficult, just annoying, just time consuming. You could expand it. I'm not going to bother to. What you'll actually end up getting is -14. And that's the slope. So I did that one quick. How do we feel about that? About this specific example, on a scale of 1 to 10. So I want to make sure that we get this before I move on to any other rules. We can always go back and do examples or more practice. Anybody still alive? Is it too much? Is it all too much for one day? Just imagine having to teach this stuff every single day. We're not finished, but I'm just going to show you one more rule just so we can start it, and I'll continue it tomorrow. Because I just want to get all the main rules out of the way. This will be the last derivative rule, and then we'll finish for the day, okay? So let us continue to our final rule. This is just practice. Practice section. Final rule for this course anyway, for derivatives, is the chain rule. This one's a little bit tricky. It's what we need to use for composite functions. So when we see one function inside another. So I'm just going to go ahead and jump to the important pieces. It's called the chain rule. When we have a composite function, one function inside the other, we do the chain rule. The pattern that I like to use to remember the chain rule is a little bit weirder than the other one. This is what I like to think about. If the original function is an outside function and an inside function, there's one function we'll see on the outside, one function we'll see on the inside, then its derivative is the derivative of the outside, keep the inside the same, and then get the derivative of the inside. This, I'm sure, is going to seem very, very weird and probably not make any sense to you right now, but just bear with me. When we see the examples, it'll become much more clear. Let me just color code these. The chain rule happens when we have a function inside the other. Let me show you what I mean, okay? Let's see it clearly with an example. Find the derivative of the following functions. First of all, I'm going to write down what the chain rule is. Derivative of the outside, keep the inside the same, get the derivative of the inside. That's what we should think about when we have chain rule. How do I know to use the chain rule for this? Well, let's look at this function. We have a function inside, and we have something going on outside. And the way I want you to think about this is to consider, let's get this separate. I want you to consider the function y equals x to the power of 5. All right? So look at this function right now. And let's consider y equals x to the power of 5. This is basically that function. Just, look at this function. It's something to the power of 5. It's just another function to the power of 5. So if we were to get the derivative of y to the power of 5, it'll just bring the 5 down. We would have an x inside, and we'd have the power of 4. Let me show you what the chain rule looks like, because it's better to do the examples than for me to talk you through it too much. Look at this. Let's look at this function. What's going on outside the function? We have this power 5. What I like to think about is essentially ignore what's inside and just treat it like it was an x. I'm going to erase that, so don't write that down. We would have 5. It would have been x, and we do our power 4. Okay? We have our same rule as if we had nothing inside. That's our first step. Bring the 5 down in front. Keep the inside the same. So treat it like our regular power rule. Treat it like it was an x. Don't touch the inside. So get the derivative of the outside. Keep the inside the same. And now get the derivative of the inside. What's the derivative of the inside? It's 2x plus 4. We got the derivative of the outside, kept the inside the same. This is the derivative of the inside. Chain rule. Tricky but easy. Yeah, that's the way I think about it. Remember, this is your rule book. If you have a function inside a function, do all the outside, do the derivative of the outside, keep the inside the same, then get the derivative of the inside. Let's do another one. I'm going to do B. I'm actually going to do C as well. I'm going to do maybe this whole page just to get it done, and then I'll do more practice tomorrow, okay? Let's look at B. This is the chain rule. I know it's the chain rule because I have a function inside. I also have something going on the outside. So look at this, the derivative. Treat this like it was x, all right? What if it was x? If the function was x cubed, what would we do? We would bring the 3 down, we would have an x, and we would have a 2 there. So it's the same idea, just keep that x the same. That x is our function now, it's the same idea. So we end up getting 3, keep the inside the same, it gets reduced to a 2. All right, the outside comes down, we don't touch the inside, and then we'll do the derivative of the inside. So the inside stays the same. And now do the derivative of the inside, just like we did here. The derivative of the inside. The derivative of the inside is 2x minus 1. So once again, it's the derivative of the outside, keep the inside the same, do the derivative of the inside. It's always the same 3 steps. That's done. That's our answer. Just hoping it feels all right. I know it's not the easiest thing in the world, but just be careful. You can compare it to this. 3, 3 and 2. You have the same patterns going on here. It's just looks different. Let's do another one. This is also chain rule. How do I know it's a chain rule? Because it looks similar to this. And remember when we did this, we have to change it to power form. All right, the function looks the same. Look at this. Y is the square root of an x. Same thing, it's just instead of being an x, it's just a whole function. So we still do the same simplification first. And now we do the chain rule. Hopefully you're still with me. I know it's new, but it's not complicated. You just need to practice it. The derivative, f prime of x, the slope function. I'm going to bring the power down in front, just like before, 1/2. What am I going to do now? Say the same thing every time. Derivative of the outside, keep the inside the same. The power, negative 1/2. The inside didn't change. Doesn't even matter what the inside was, really. You'll notice I do the outside first. I don't even worry about the brackets until after. And then I get the derivative of that. The derivative of the inside. 5 plus 2x. No need to simplify that. That's the final answer. I will write out the alternate, but you won't be expected to have to write it like this. All right, I just want to get all these answers out of the way. I'm just going to do D so we can have it, and then tomorrow I'll go and do a bit more practice. What am I going to do? Well, this is a bit of a weird one. I definitely know it's chain rule. The problem is, how do we deal with it? Well, the form is like this. It looks like that, so the first thing we're going to do is bring that power up. So we can do the same thing. Bring the whole thing up and change the power. I'm going to try the derivative now. The derivative is do the outside first. Take the power, bring it in front. Negative 4. Keep the inside the same. Reduce the power. Okay, that's the first step. The inside doesn't matter. It could be anything. I'm just going to copy it. And now I get the derivative of the inside. It's 2x. Okay? That's our final answer. You can simplify this, but you don't need to. I'm not asking you to simplify that too much. What it would simplify to is this. I'm going to show you. All right? That's enough for one day. we covered a lot. We reviewed the delta process. That was what we did yesterday. We did a little bit of applications of that. We did the constant rule, the power rule, the chain rule, sorry, the product rule and the quotient rule, and the chain rule. So lots to think about, but none of the topics are all that difficult. We'll just have to do a bit more practice to make sure that we know what each rule is. But that's it for the derivative rules. The rest is just applications. All right. So starting, not tomorrow, starting Sunday, we'll do a bit of practice on that. Okay. Happy Thursday, everybody. I'll stop the recording anyway. Happy Thursday to you guys too.